Hello there, Period 4 Calculus, and welcome to a video discussing the applications of mathematics in a video game. That video game being Black Ops Zombies, which some of you have heard of and some of you have not. So if you aren't familiar with it or need a refresher, I'll explain what the game is about first, since, well, nothing I explain past here will make sense otherwise. So, how it works in the easiest possible way to understand. You, the player, are trapped in some location surrounded by undead. A certain amount of zombies appear each round, coming from these things called windows. The player is forced to exterminate the round's worth of zombies in order to progress through the game. As the round number increases, more zombies spawn in with more health, and the goal of the game is to survive as many rounds as possible. Pretty simple, right? Well, despite it being so simple, I've wasted thousands of hours being unproductive within this world of running in circles for no reason. And I've noticed a few things that could be useful for this project. So, in this video, I'll be discussing how the game and its players use three forms of math taught at the school: trigonometry, calculus, and computer science. In that order. So let's get started. My first subject here is on the usage of combinations, or as many of you know it, this little thing on your calculator. You may have learned about combinations either in trig or earlier, so hopefully you're all familiar. Believe it or not, I actually used this formula in my gaming even before we were assigned this project. It's weird, I know, using math outside of school willingly. So what's the point of using this formula? Well, it's needed for finding out the chances of getting the correct window spawn points on the top floor on 5. None of you know what I mean by that, so it's time for some more context. 5 is one of the playable maps in the game. The top floor of the map is where the player does a high round strategy, aka the best way to play the map when aiming for high rounds. There are 6 windows in this room, only 4 of which are active at a time, meaning only 4 can have zombies coming out from them. The windows that are active though are completely random. In this image here, I've labeled each window with letters. In one match, the active windows could be A, B, C, and D, whereas in another match, the active windows could be B, C, E, and F. The combinations aren't restricted to only those examples though. There can be combinations using any 4 of the 6 letters. Anyway, through copious amounts of time wasted, I managed to find a trigger to change the active windows during the same match. I won't explain what that trigger is, since you just had way too much information thrown at you, but the active windows that a player going for high rounds would want would be A, D, E, and F. So that one window setup is the only one that you'd be able to run the high round strategy with, making all other setups useless. I'll say that again. The only combination that you want of the windows is A, D, E, and F. How many total possibilities of active windows are there though? That's where the combinations formula can be useful. One can figure out how likely they are to get the correct window setup with each triggering of window randomization. Hopefully that made sense. I don't know if it did, but let's get to the math now, because math is fun. Right, here's the combinations formula, indicated by the giant C there. The N represents the total amount of windows in the room, which is 6, and the R represents the total amount of windows active at a time, which is 4. So if we do some high-tech plugging in of numbers and actual math, we can find out that there are 15 possible window setups. Of these 15, there's only one that allows a player to run the high round strategy. So if we divide 1 by 15, we find that the chances of getting the proper window setup upon each triggering is a little less than 7%. Yeah, not bad. Actually, it's kind of bad. That is one usage of math within the game of zombies. I don't expect any of you to have retained any of that, but let's move on to the next subject, which involves derivatives. Fun, I know. So as you should have remembered, the goal of this game is to play for the ever-increasing round number in the bottom left corner. That thing, yeah. There's more to just playing this game alone though. One can actually waste time with up to 3 other people. That being, there are 4 possibilities for the amount of players. 1, 2, 3, and 4. I know, amazing. Each of these having a different amount of zombies per round. Very important there. In each mode, there are a different amount of zombies per round. So let's think in theory here. One would imagine that when playing alone, there's say 1x amount of zombies. When you're playing with another person, so 2 player, there's 2x amount of zombies. When you're playing with 3 players, there's 3x, 4 players, 4x, yeah. But that is not the case. Through the power of derivatives, though, we can find out the truth. The truth being what number of players it would be most worth going to a high round with. What I mean by this is if there's 1 times the amount of zombies for solo, but only 1.5 times the amount of zombies for 2 player, it would be more worth it to go to a high round 2 player. The concept may be a little weird, but that's just part of the game. I really can't explain the logic any more than that because there's these beautiful formulas on the screen right now. So as you can see, these are the formulas for the amount of zombies per round in regards to the number of players. What we're going to do now is find out the acceleration of the amount of zombies per round by differentiating each of these formulas. So, differentiation. Fun. Let's do it. Math, it's happening. Cool, and we're done. We've got some pretty random looking numbers here, so let's divide each of them by the amount of players to see the true differences between each mode. Each number will be the acceleration of the amount of zombies per round per player. The highest number will be the least preferred mode, while the lowest number will be the most preferred mode. So, the results. We can see that the acceleration for the amount of zombies is not exactly equal to each other for the amount of players. Solo seems to be the most worthy game mode, followed by 2 players, then 3 players, then 4 players. All thanks to derivatives. We figured it out. Yay. Let's take this one step further though. Say we were to take the limit of the function as x approaches infinity. Given a graph of the function, you'd know pretty easily that it just goes straight towards infinity, right? Well, that would be the case, but in the realm of video games, things don't work out quite as well as in theoretical calculus land. I don't know what I'm saying. To demonstrate what I mean more clearly, we're going to take a different graph that looks the exact same as this one, which is zombie health. The limit of zombie health as x approaches infinity would also theoretically be infinity, but in reality, it is not. Zombie health is measured by one of the simplest formulas you could probably think of. This. And as you should remember from the beginning of the video, which you didn't, zombie health increases every round. So x in this represents the previous round's health. This formula is put into effect at round 9, at which point their health is 950 HP, is what we'll call it. So going to round 10 from 9, multiply 950 by 1.1 and get 1045, that's the amount of health on round 10. So they get stronger and stronger until the point where pretty much no weapon can kill them anymore, until their health breaks. For those of you that took the computer science course here, you're probably familiar with this. This is an int. Kind of the first thing we were taught ever. The maximum input for an int is this big old number here. Zombie health, also, is stored in an int value. So what do you think happens when zombie health reaches that number? Well, as I said earlier, the game breaks. Sort of. On round 163, zombie health exceeds that big number up there. But because it's an int, it can't. Zombie health on round 163 is instead reduced to that of round 1 health. So, as you could guess, that's a really tiny number, and things are fun. On round 164 though, the health does not just become equal to that of round 2. It doesn't follow the formula where you take 1.1 multiply it by previous round health. Instead, the health is just that of round 162, and thereon after switches between round 1 health and round 162 health every other round. So if we were to take the limit of zombie health, or zombies per round since they're the same thing, as x approaches infinity, we would get that the limit does not exist. And it's not infinity either, because infinity not exist too. Yeah, okay. Why is this? Well, as we learned back in chapter, I don't remember, if there is oscillation, the limit as x approaches infinity does not exist. And you can see this function doing a lot of oscillation stuff. Yeah, it's right there. So yeah, video games are just here to tell you that everything you've ever learned in calculus is a lie. Everything. That's it though. I really don't expect any of that to have made much logical sense to anyone unfamiliar with the game, but I hope you at least enjoyed watching. Yeah. Thank you for sitting there doing nothing, and goodbye.